Good morning. My name is Johansson and my register number is URK25CS1019. This is practical number 12 for the course Partial Differential Equation, Vector Space and Laplace Transformation for Computer Science and Engineering. In this practicum, I will explain how Laplace transform is used to solve differential equations in real life computations. The Laplace transform is used to convert differential equations from the time domain into the S domain, where solving equations become easier. After solving, we apply the inverse Laplace transform to convert the result back into the time domain. First, let us consider question 1, which analyzes network traffic burst. The system is modeled using a first order differential equation where the rate of change of the number of packets plus 2 times the number of packets is equal to an exponential decreasing input. This represents a situation where a sudden burst of packets arrives and then gradually reduces over time. Mathematically, the Laplace transform is applied to both sides of the equation. The derivative term is converted using the property that the Laplace of dn by dt becomes s times n of s minus the initial value. The equation is then rearranged to solve for n of s. After obtaining this expression, the inverse Laplace transform is applied to get n of t, which gives the time-based behavior of the packet q. In this Python program, we first import the SymFile library, define symbols for time and Laplace variables, and represents the initial condition. Then we compute the Laplace transform of the right-hand side exponential function. After that, we construct the transformed equations using Laplace properties, solve for the Laplace variable, and finally apply the inverse Laplace transform. The heaviest side of function is removed to simplify the result. The final output shows how the packet queue initially increases due to the burst and then decreases as the system stabilizes. Next, in question 2, in the question 2, we analyze the motion of an autonomous delivery robot. The system is modeled using another first order differential equation where the rate of change of deviation plus 3 times the deviation is equal to a decaying exponential signal. This represents how the robot corrects its path gradually while external disturbance reduces over time. Again, we apply the Laplace transform. The derivative is converted into an algebraic expression in terms of s, and the equation is solved for x of s. Then the inverse Laplace transform is applied to obtain x of t. The resulting function represents how the deviation decreases over time, showing that the robot stabilizes its path. So in the Python code, the same procedure is followed. Symbols are defined. The Laplace transform of the input is computed. The equation is formed using Laplace properties and then solved symbolically. The inverse transform gives a final time domain solution and the heavy side function is removed for clarity. So, in the third question, we consider a second order differential equation representing an autonomous downwards motion affected by acceleration, damping, and restoring forces. This equation includes a second derivative term, a first derivative term, and a proportional term, along with an exponential disturbance input. In this case, the Laplace transform of the second derivative is used which becomes s squared times x minus s times the initial position minus the initial velocity. Similarly, the first derivative is transformed into s times x minus the initial position. These expressions are substituted into the equation, which is then solved for x of s. After solving, we apply the inverse transform to obtain x of t, which describes the robot's position over time. The solution typically shows that the system responds to the disturbance and gradually stabilizes due to damping and restoring force. In the Python implementation, we define additional symbols for initial position and velocity. The Laplace transform of the input is computed. The transformed equation is constructed using the properties of derivatives and then solved symbolically. Finally, the inverse transform is applied to obtain the time domain solution, and the heaviside function is removed. And that's it. Thank you.